In this video, I'm going to show you how to find the argument and magnitude of a complex number. So I'm going to first choose a complex number. So I'm going to call it Z, and I'm going to write it as 1 plus 2i, with the real part being 1 and the imaginary part being 2i. Okay, so if you have to graph this, you need to have the real and imaginary axis. First, I'm going to draw the two axes. So this part is the real part of the complex number, and this one is the imaginary part. So the real part of the complex number needs to go on the real axis. So it's going to be here 1 unit, 2 units, and 3 units on the real axis. And then you have 2 units on the imaginary axis, so we're going to say 1, 2. So 1 on the real and 2 on the imaginary is the dot here. And to draw the complex number, you always start from the origin and then you draw the line till you join the complex number. Okay, so this is the complex number Z. All right, and you will see that the complex number has an angle with the x-axis. So this angle here, this is called the angle theta, and theta is actually the argument. Okay, the argument of the complex number Z. Now the argument and the angle of the triangle which is formed here. So if you drop a line here, you actually get a right angle triangle, and this is the angle of it. So there's a difference between the argument and the angle of the triangle, because the argument is not always the angle of the triangle. So if we have to define the argument of Z, we can say that it's the smallest angle from the positive x-axis. Okay, so we're going to have that as definition, and this is going to actually help us to find the argument in 3 other scenarios. So that's the first scenario where you have 1, 2. So 1 on the real and 2 on the imaginary. So the number, the dot is here, that's the line. And the smallest angle from the positive x-axis, that's theta. So this is actually a right angle triangle with this being the angle. So actually just draw, okay, let me just do it here. So this is 1 unit, this is 2 units. And if I have to label, this is actually going to be the opposite. This is going to be the hypotenuse, because it's, next to the 90 degree, and this is the adjacent. Let me draw it separately so that it's a bit more obvious. So you have a 90 degree angle here. This is 1 unit. This is 2 units. And you need to find that angle. So that's O, because it's opposite to the angle. That's H. That's A. So you have O and A. And if you use SOHCAHTOA, when you have O and A, we usually use tan. So tan theta is O over A. Tan theta will be O being 2 and A being 1. So theta would be arctan of 2, which is 1.107 radian. Okay, arctan is the same as tan inverse. So this is how you find the argument of the complex number if it is found in the first quadrant. So here. What we're going to do next is I'm going to try an example whereby it's not in the first quadrant. Okay, so I'm just going to erase that one. And I'm going to show you one whereby it's not in the first quadrant. So I'm just going to draw the axis again. So now the complex number Z is going to be minus 1 plus 2i. So it's minus 1 on the real axis and 2 on the imaginary axis. So from the origin, that's the complex number. Okay, just erase that. So this is minus 1, and this is the angle. You see that I'm not writing it as theta. I'm going to explain to you why. So by definition, the argument is the smallest angle from the positive x-axis. So from the positive x-axis, if I move, this is actually the argument of z. So you can see here that the argument is not the angle of the triangle. And the triangle here is still the same triangle with the opposite being 2 units and the adjacent being 1 unit here. So to get alpha, you still do tan inverse of 2/1 and you'll get the same answer as in the first part, which is 1.107. However, the argument here, argument of z, is the whole angle of the straight line, which is pi, minus 1.107, because this is 1.107. So to get the argument, you do the whole angle, which is pi, minus this small angle, which is minus 1.107, and you get 2.035 radian. So this is what you would do if the complex number was found in the second quadrant. And now I'm going to show you what you would do if it was in the third quadrant. So I'm just going to erase that. And then I'm going to draw one whereby the complex number is -1, -1, -2. So that the complex number is here in the third quadrant. So I'm just going to actually draw that one again. All right, it's here. So this will be alpha. Okay. So the argument now, if you look at the definition, it's the smallest angle from the positive x-axis. So if I turn anti-clockwise, the angle is quite big. It's not the smallest angle from the positive x-axis. However, if I turn clockwise, this angle is smaller. So the argument is actually you turning clockwise. However, if you turn clockwise, so if you have a clockwise turn, you need to include the minus sign because you're doing the reverse of the other one. So if you need to get this angle theta here, first of all, you need to do pi minus 1.107. If you do pi minus this small angle, which is 1.107, you get this theta. But since we are moving in the opposite direction, we actually need to put a minus there. So it becomes minus pi minus 1.107, and that becomes minus 2.035. Okay, so this is what happens when it is in the third quadrant. And now I'm going to do a last one, whereby it's in the fourth quadrant, just for you to see how things change. I'm just going to erase that. And now let's draw it in the fourth quadrant. So in the fourth quadrant, I'm moving 1 on the real axis. On the imaginary axis, I'm moving -2. So the point is here. I draw the line again. And what will be the argument? If you move anti-clockwise, it's quite a big angle from the positive x-axis. However, if you move clockwise, it's a very small angle. So the angle of the triangle was 1.107. Okay, but since we are moving clockwise, it's minus 1.107. So for the last one, we actually don't need to do any workings. It's quite straightforward.